Justin, thanks so much. And it's nice to be here today. Similar to what Kelly said, it's been about 2 years since I did the seminar, so it's exciting to be here. And I'm going to tell you what the Tg is. It's a glass transition temperature, and I'll talk a little bit more about that in the next 10 minutes before we get to the Q&A for everyone. A brief extra introduction, as I'm an assistant professor of material science and engineering. I joined the University of Central Florida in 2017, and my research in general focuses on looking at a mission of human sustainability through education and technology. And through our mission, we've developed values for our research lab where we focus on healthy well-being, which I believe opens the window for additional creativity and allows us to engage in large transdisciplinary projects that bring together multidisciplines to develop new things. What our vision in terms of research initiatives are to minimize our footprint by using sustainable electronics and soft materials. And so pictured here is a relatively recent image of my research group. And you can also see more details at my webpage at kcrawfordgroup.com. And you can follow me on Twitter or email me if you have questions later. Now, our research group has worked on a number of different projects over the last few years. And of course, there's not enough time to talk about all of them in the next 8 minutes, but I wanted to at least highlight a little bit about what we're doing in case you're interested in having some conversation offline. The first one that I want to point out is related to polymer microfibers. This is an exciting project for me because it's completely designed and developed and led by undergraduate students here at the University of Central Florida. They're getting ready to publish a paper on building a centrifugal force spinner to create polymer microfibers, and then optimizing the instrument and running different parameters, and then publishing the work that they found, which can be applied for a number of different applications. So I'm very proud of the undergraduate students who have been working on this for a little more than a year. And then the other thing in regards to sustainable electronics and looking at soft materials is having electronic devices that can be bioresorbable or degradable to some degree in either our body in terms of implantable electronics or in the environment. And then with that on the top right, and energy harvesting, this is a way where you apply mechanical input and you can get a voltage output. So if we can optimize this, then it could potentially in the future be integrated into other electronic devices to have a closed loop, power energy system. And we look at other factors in transient electronics. These are resorbable electronic devices that have a large amount of soft material. And because you have a mechanical mismatch between the metals that are incorporated in the soft material, you tend to get delamination. And that's something that we look at in terms of points of device failure, so we can identify ways to improve our transient electronic devices. One other of the two areas listed on this slide is on electro-optic or nonlinear optic polymers. This is also an important area to study in thinking about the sustainability of humans through technology, because this allows us to have faster or more efficient telecommunication and quantum information technology applications by developing these nonlinear optic polymer materials. And then also we have a project related to the development of a high tiara level wearable health monitoring tool to assist firefighters in on-duty firefighters. And then I will probably be talking about this at some point later, but what I want to focus on for the remaining of the minutes that we have is our efforts to develop new monomers that allow us to create new polymers that might have useful applications in electronics and beyond. And the reason why I want to focus specifically on the new monomer project is because I feel like there's some information that's important to share about some of the materials that are used in the polymers that we use every day. So for example, on the left, you see a monomer, it's called bisphenol A. You might have heard of this abbreviated as BPA, and that all of our water bottles or plastic containers now that have food contact all generally say BPA free. And that's because we know that BPA is an endocrine disruptor, particularly in the estrogen hormone. But the thing is the polymer that originally included BPA is really useful. It's favored because it has high temperature stability and good optical transparency. But instead, we have replacements like bisphenol S that has a similar shape, and the fluorine-9 bisphenol, the BHPF. And these replacement materials are used in everything from medical devices and membranes or high temperature applications and packaging, food packaging. They're used in energy resources and other industrial applications. Again, because they have really good high temperature stability and efficient optical transparency. In fact, in the case of BHPF, you have higher than normal refractive indices for when considering those optical properties. The reason I want to focus on these is because if you notice the location of these hydroxyl groups, these are the OH bonds here and here, that for the bisphenol S and the BHPF, they're kind of in a similar location. So when we take a closer look at estradiol, which is the estrogen hormone where BPA fits in there, you see that the overlap with the OH groups is really close. And this is one of the reasons why the BPA and also BPS and BHPF are actually endocrine disruptors. So these will cause things like neurological difficulties, developmental difficulties, reproductive issues, diabetes, cancers, obesity, and the list is even longer than that. The problem is that even though our commercial devices now are BPA free, it doesn't mean they're not BP something else free, and that those materials may also be causing endocrine disruption. And in fact, there's multiple literature articles to report and show that these actually do have endocrine disruption. So here's a Nature Communication paper from a different group that I've referenced to motivate this work that shows a simulation that the BHPF fits inside the estrogen receptor and causes endocrine disruption. And there are multiple papers as well showing that BPS is also an endocrine disruptor. This is a big issue for us because these molecules have not been banned or regulated, at least here yet. And so our group decided we would tackle this in two different ways. One, there's a sustainability issue of once we're done with the polymer materials, how do we deconstruct them for later recycling or to be resorbed into the environment, assuming they would be non-toxic. And the other is that if we could potentially use these same properties of this large bulky group and these sulfone groups are part of what give the high temperature stability and good optical transparency. But if we could move the hydroxyl groups away from this aromatic ring, then we might be able to prevent them fitting into this receptor location and they won't cause endocrine disruption any longer. So that's our hypothesis. The short version of that is we're still in the preliminary stages of identifying if this is if these are endocrine disruptors or not, our modified monomers. But I wanted to share with you at least the preliminary data that we have today. So the first thing we did was we took the fluorine and sulfone diol derivatives, and we extended the hydroxyl group away from the aromatic ring, just as I suggested. And then in addition to making these diol derivatives, we also made a diacid derivatives with a fluorine diacid and sulfone diacid. And the reason why we did this is because we can polymerize the materials together by joining diol groups and diacids. So we could join the fluorine diol and the fluorine diacid and make a polymer, or the fluorine diol and the sulfone diacid and make a polymer, and so forth. And so we'll just briefly show you a couple of examples that we've made in our lab to demonstrate that these monomers can be polymerized and that we can, to some degree, control the glass transition temperature. Now that Tg, or glass transition temperature, is important because it represents the upper service temperature available for a product. And this is important in the industrial processing of these materials. And so the glass transition temperature here for the initial two materials is about 93 and 70 degrees Celsius. So that's much higher than room temperature. And we can begin to control the glass transition temperature further by controlling the flexibility of the backbone polymer chain. So you see this 70 degrees is much lower because this larger number of carbons allows for greater flexibility, which means that less energy in the form of heat is required in order for the chain to become flexible, which is the Tg that comes as an output of that, versus the shorter carbon chain that restricts flexibility. So you have a higher glass transition temperature. We also polymerized together the 2-fluorine diol and diacid monomers. And then we did the same thing for the fluorine diacid and the sulfone diol as well. And we did the same thing for the sulfone derivatives too. We put a short chain ethylene glycol versus the 6 diol, the 6-membered carbon diol. And you notice that maybe you noticed that the glass transition temperature for the sulfone groups is overall smaller, 78 and 40 versus 93 and 70. That's because this sulfone group is less bulky than that fluorine group that restricts backbone flexibility. We did the same thing by pairing the sulfone with the fluorine matcher for acid versus alcohol, and then put the 2 fluorine monomers together as well. And so an important thing to characterize here, or 2 additional important things to characterize is, 1, do they still have high temperature stability? And so we measured the thermogravimetric analysis, or the TGA, that shows us indeed most these have high temperature stability despite their chemical modification. And so for frame of reference, most organic polymers tend to degrade above 200 degrees Celsius. And so these polymers are robust up until about 400 degrees. And even though this red ethylene glycol derivative looks to be degrading a bit earlier, statistically, it's insignificant when we ran multiple trials. Then another important component is that we maintain the optical transparency. This is really important for a number of applications, including in electronics. The fluorine derivatives are 1.64 on average for the refractive index, and the sulfone is a little bit lower. For a frame of reference there, the typical polymer is around 1.4 to 1.5 refractive index. And so a small jump of 1.6 might seem insignificant, but it actually can enable it for a number of applications that wouldn't otherwise be available for the lower refractive indices. So just to kind of sum this up, we're right in the middle of measuring if these monomers actually do cause endocrine disruption, which we're hoping they don't, but we will find this out shortly through a collaboration with Professor Tom Keene and the College of Medicine, who's doing these studies for us. We also want to see if we can actually degrade them. They have ester linkages, so they should be able to degrade. We're about halfway through the study, and we're finding that they do have degradation in film form, and I'll be able to report on that soon. And then, of course, we want to integrate these materials into electronics, assuming that they don't have any biocompatibility issues. And so that's something that we're looking into as well. So I'm happy to answer any questions you all have about the monomer project or any of the other projects that I briefly brought up today.